Section 6.2 is about compound interest. I want to compare compound interest to what we've done with simple interest, so a quick review. $50,000 invested at 9% nuts per year for 3 years with simple interest. I get 9% in the first year, which is $4,500 of interest. And then I get the same interest, 9% on the same $50,000. I get another $4,500 in year 2. And in the third year, another $4,500 for a total of $63,500. To discuss compound interest, we're going to take the same $50,000. We're going to invest it at 9%, but now we're going to allow the 9% to compound annually. So here's how it works. The first year, nothing looks much different. You get 9% interest, which is $4,500. But at the end of the year, that $4,500 gets added into the balance. And from here on out, you'll be earning interest on $54,500 instead of the original $50,000. So this interest gets to earn its own interest. So when we go into the second year, we're going to have 9% interest on $54,500. Now we're going to make $4,905 of interest. And compared to what I got in the first year, I get another $405 of interest because last year's interest is allowed to earn interest. So I add this onto the balance from the end of year 1, and now I have $59,405. And then during the third year, the original $50,000 gets to earn interest, $4,500 from the first year gets to earn interest, and $4,905 from the second year all gets to earn interest. So I have 9% of $59,405. That third year's interest amount is $5,346.45 for a grand total $64,751.45. So you can see how compared to simple interest, compounding is a lot better to let your interest earn interest. I'm going to go back and do this again, but a little bit faster. After the end of the first year, I will have my original 100% of my $50,000, plus I'll have 9% interest. So I will have 109% of my original principal. I can do that in one calculation by multiplying by 1.09. So if you take $50,000, multiply it by 109%, you will get immediately to the $54,500 number. So each time the money moves forward, you multiply it by 1.09 for 109% of your money. Well, then from year 1 to year 2, if I multiply by another 1.09, 1.09 this time times the $54,500 number, I get directly to the $59,405. And then multiply by 1.09 again, I will get to my total of $64,000. So instead of stopping and adding up the individual interest all along the way, I can kind of do it all at once. Now I'm going to make it even faster. I start with $50,000. To move it to the first year, I times by 1.09. And without stopping to calculate this, I'm going to move from the first year to the second year, multiply by another 1.09. From the second year to the third year, multiply by another 1.09. In math notation, that would be 50,000, 1.09 cubed. So for 3 years, or 3 times, 3 arrows moving the money forward, 50,000, that will give me the same $64,751.45. So from this, we learned that compounding is good. So I'm going to compound more often. I'm going to take the same $50,000 investment and the same 9% per year, but now I'm going to compound semi-annually, so every 6 months. So I'm not going to have an arrow that goes, I'm not going to push the money clear till the end of the year. I'm going to stop after 6 months and figure out my interest, and then I'll move it forward for another 6 months. Okay, so the 9% was for the whole year. Well, then now that has to be divided into 2 equal pieces. So it'll be 4.5% for the first 6 months and 4.5% for the next 6 months. So each one of these arrows needs to be 104.5% of the original investment. So I take the 100% of my principal and I add on another 4.5%. So each arrow will multiply by 1.045. Multiply again by 1.045. So each time I advance the money 6 months, I multiply by 1.045. So when you compound more often than once a year, you need to figure out your interest per period, which will be your annual interest rate, and then divided by the number of times you compound within a single year, which in this case was twice. That gives me the 0.045. And then the total number of periods will be 3 years times 2 times per year, which would be 6. So I'll take my original principal, and each arrow that advances the money is 1.045 for an interest factor. And I will have 6 of those, 6 periods throughout the course of that 3-year investment. That gives me a total $65,113.01. So you can see that compounding just gets better and better the more often I do it. However, there's kind of a law of diminishing returns. So let's do this one more time, and then we'll go to Excel. What if you compounded every day? I need to know the interest per period and the total number of periods. Interest per period will be 9%, that's for a whole year, but now you have to divide it into daily pieces, so that would be divided into 365 compoundings per year. Each day's interest rate is 0.000246575, and there are more decimal places, so either store this or use 0.09 over 365, but don't round it off or else your answer is going to come out wrong. Those decimal places all end up mattering a lot. The total number of periods would be 3 years times 365 days per year. That's 1,095 times. So now if I'm picturing a number line, here's 0 and here's the end of year 1, you've now got a whole bunch of teeny tiny little arrows just advancing the money one day at a time at a little fraction of an interest rate, and you're doing this 365 times each year for 3 years. I can get to my total pretty quickly by starting with my original principal and multiplying it by 1 for 100%, plus my daily interest factor is 9% divided by 365. This is plus the 0.0246% more. And then I have to do that for the total number of periods in all 3 years, which is 1,095. I got $65,496.04. So even though I went from 2 times a year to 360 times a year, I've only gone up about $380 over the total over all those years. And even if I went to like compounding it every second, it doesn't get a whole lot bigger than this. In fact, in mathematics, there's something called compounding continuously. And when you compound continuously, you don't talk about how many arrows there are. Now there's like an infinite number of little arrows, and you get just this little tiny fraction of interest rate. Your formula totally changes, where your future value is your principal times the magic number E, it's called the natural number E, raised to the annual interest rate times by T. So this is for infinity compoundings per year. And all of our formulas break down when we try to plug an infinity into the formula, and that's where this E comes into play. So here's how it works for continuously compounded. You take your principal, 50,000, times E, and there is an E key on your calculator somewhere by the LNX key, or your LN key. You should have a key that says EX. So be E raised to the, take the full annual interest rate of 9%, multiply up in the exponent by the number of years. In this case, 50,000 E to the 0.27 is what the exponent will simplify to become. which will give you $65,498.22. And that's if you compound every second, every fraction of a second, every moment. In the course of 3 years, you only get $2 more than if you only compounded daily. But this formula, called the PERT formula for obvious reasons, it applies for compounding continuously, and that means you have lots and lots and lots of compound periods every year. I'm going to teach you how to use Excel to do these problems, and then Excel can be your calculator. Excel uses several variables, and we just need to understand where they fall on the number line. So at time 0 is PV, which is your present value. And then wherever you end, the amount of money at that point is your future value on the last day of the investment. And then you have the option, which will come up in sections 6.3, 6.4, and 6.5, that you could make payments along the way at regular intervals, regular size. And for our purposes in this class, your last payment will always fall on the same day that you want to add up your future value. So we call this the end of the period, that the payment doesn't start at time 0, it comes at the end of the period. Those payments can add on to your investment, in which case they're deposits, or you could take away from the amount that you have in the bank. They could be withdrawals. So your payment could be either a positive number or a negative number. In section 6.2, the payment is always 0. We're not adding in any extra deposits or taking out any withdrawals. But that will come into play in 6.3 and 6.4. Then we have an N per, which is the total number of periods, which is the same as saying the total number of payments that are made. So how many of these extra payments did we have, or how many arrows did we have advancing the money? And then lastly, this one's so important, it's getting done in red. It's an interest rate, but this is the interest per period. So if it's compounded, you have to divide your annual interest rate by however many compoundings per year. So I like to put in an extra variable, which I just call the compoundings. So it's the number of periods in 1 year. Okay, let's pull up Excel and put Excel to work. I'm going to want the future value, which is FV. I want the present value, PV. I want the annual rate. I want the number of years of the investment. Those are the, and the payment amount, if any. So again, in this section, we're not going to be adding or subtracting anything from our original principal, so our payment will be 0. Then we're going to calculate the number of periods, which is called N per, and then we're going to find the rate per period. To redo our example, we're trying to find the future value, so that will stay blank. The present value will be 50,000. The annual rate was 9%. The number of years of the investment was for 3 years, and the payment was $0. Okay, now the total number of periods needs to be calculated. That will be once per year. I need to go back and add in a variable for the number of compoundings. Since this is annual compoundings, I'll have once per year. Then my total number of periods will be 3 years times by 1 time a year for a total number of 3. So 3 arrows advancing your money forward. Your rate per period is your annual rate divided into, well, just once per year. So that should still be 9%. Okay, now for the future value, I can calculate it. Excel has some formulas built in, and the formula for future value is called FV. Notice that it comes up, there's one that's FV and one that's FV schedule. We use the regular FV, and to select that, you can hit the Tab button. And then notice that when I hit the tab, it put a parenthesis in here. And then I also have like a template for what information Excel needs in order to figure out the end value of this investment. First thing it wants is the rate. That is a rate per period. It's not the annual rate, it's per period. Number of periods was 3. Then it wants the payment, which is nothing, no additional deposits or withdrawals. Present value was 50,000. And then type is either at the end of the period or at the beginning of the period. I will leave the discussion of the difference of this to your Finance 3100 teacher. For our purposes in this course, all we ever do is end of the period. That's what Excel will default to. If you want to select it, you can type a 0 to select this option. And now when you hit enter, it says $64,751.45, which is what I got when I did the analysis before. Let's try it again. Let's do that same problem, the same $50,000 example that we started with. Future value, I'm still trying to find. Present value is still 50,000, annual rate 9%. But now the compoundings, compounded semi-annually, that will be 2 compoundings every year. Number of years is 3, payment. Okay, now for the total periods, I would need to have 3 years times by 2 compoundings each year for a total of 6. So compoundings per year times number of years. Rate per period will be my annual rate, but now it needs to get divided into however many compoundings you have each year, that many equal pieces. So 0.09 divided into 2 equal pieces, there's the 4.5%. Then my future value will be FV, tab to get that formula active. Notice it puts the parenthesis in for me. First thing it wants is the rate. That's the rate per period. Separate with a comma. Total number of periods is 6. Payment amount, no additional deposits or withdrawals. Present value, 50,000. And the type, you can either put a 0 or you can just leave it blank and Excel will assume it's a 0. So at this point I can just say enter. 65,113 and 1 penny. There it is, 65,113 and a penny. For compounding daily, now that I have everything set up, if I just change the compoundings to 365 compoundings per year, these other 2 cells were built on that cell, so it should automatically update my total periods and my rate, which it did. There's the 1,095 and my interest rate, which looks like it's rounded, but it's not. Excel is going to keep all of those digits in there. And it updated my future value also. There it is, 65,496.04. For compounding continuously, mathematically you would change to an E. You can get around that by just saying you're going to compound a lot. So just change the 365 to like instantaneous compounding. I'm going to put 500,000 compounds in there and then see what happens to the total number of periods. Rate per period went to scientific notation. There it is. And then here's my total value of the account, 65,498.22. There it is. Okay, let's go to WebAssign. Okay, the first problem just wants me to identify some variables. So I'm taking 9% is going to compound monthly for 7 years. So for the annual interest rate, and as a percent, that would be 9%. Length of the investment in years is 7. The periodic interest rate, so that's the interest per period. I will need to take the annual rate of 9% and divide it by the number of periods, and that was monthly compounding. So divide by 12 will give me 0.0075. As a decimal, to make it a percent, you move the decimal 2 places. So it would be 0.75%, and that's a per month. Total number of periods of the investment, well, 7 years of monthly compounding. So the total number of periods will be 7 years times 12 months per year would be 84 months of compounding. Okay, let's look at question number 2. What is the future value if $9,000, that's my present value, is invested for 8 years, 10%, and then semi-annual compounding? I'm trying to find the future value, so that will stay blank. The present value will be 9,000. The annual rate is 10%. Compoundings that's per year, and this was semi-annually, so that would be 2 per year. Number of years was 8. Payment will be 0 in section 6.2. Total number of periods will be 8 years times 2 compoundings per year for a total of 16 different compounding periods. The rate per period is the annual rate of 10%, but then it has to be divided into 2 equal pieces. So 5% every 6 months for a total of 10% over the course of a year. Future value, pull up the FV formula. I need the rate, which is the rate per period. Number of periods, 16. Comma, payment 0, present value $9,000. The type, you can either just leave it blank and Excel will default to a 0, or you can take control of your life and put the 0 in there. $19,645.87. Don't worry about the fact that you have parentheses around it and that Excel thinks it's negative. We will deal with that in the next section. $19,645.87. Number 5, what present value? So we're looking for the present value amounts to $25,000. So that's after the investment is done. That's the future value. What present value amounts to $25,000, 10 years, 7% annual compounding? All right. My future value is now known. That's going to be $25,000. Present value is what I'm looking for. Annual rate was 7%. Yes. Compoundings once per year, annual compounding for 10 years, no additional payments or withdrawals. Total number of periods will be 10 years of 1 per year. Rate per period will be 7% divided into 1 per year. And then to find the present value, I don't want to use the FV formula because I already know the future value is $25,000. I wonder what the formula in Excel for the present value would be called. Well, you're right. It is PV, but I need an equal sign to call it up. Equals PV. There it is. Returns the present value of an investment. That's the one I want. Rate per period, 7%. Okay, now I could, just for the record, I could type that in. But once you've got this all built, it's so much easier just to point and click. So rate 7%, number of periods is 10, payment, nothing extra, future value, 25,000, type, have it default to a 0. Oh, I gave it 70% interest. Huh, no wonder. That's why you don't type it. You should really just click it. Okay, let's try that again. $12,708. That sounds better. So if I take $12,708.73 and I invest it for 10 years at 7% and it compounds once a year, At the end of those 10 years, I will have $25,000. Let's do number 11. I'm going to do it two ways, one by hand and one on Excel. A machine is valued at $10,000. That's its value right now. So it'd be like a present value. If the depreciation at the end of each year is 30% of its value, so it loses 30% every year, find the value at the end of 4 years. So my mind sees this. In the first year, it's going to lose 30%. So that means its value will be 100% of the beginning value, but take away 30%. If it loses 30%, it's going to keep 70%. So you're going to times this by 0.7, and after 1 year, its value will only be $7,000. And then for the next year, that $7,000 is going to lose 30% more. So if it loses 30%, it keeps 70%, and now it will only be worth $4,900. I can make this go faster if I just start with the $10,000 and I think of 100% minus 30% every year for 4 years. That would be 10,000 times 70%, make it a decimal, to the fourth. After 4 years of that depreciation, your final value will only be $2,401. Okay, how would we do that in Excel? Well, I'm glad you asked. We're trying to find the future value. The present value is 10,000. The annual rate, okay, this is a rate of interest. So Excel expects a positive number, but if it's declining, I'm going to put in a negative 30%, so it's losing 30% of its money. Compoundings is at the end of each year, so every year it loses 30% from the previous year for 4 years, and no additional devaluation going on. Total number of periods, 4, the same as the years, and the rate per period, losing 30%. Future value equals, to put it into calculation mode, future value with a tab, interest rate per period, lose 30%, comma, for 4 years, no additional payment, start out with a value of 10,000. You can have it default to 0 for the type, and there it is, 2401. And notice that Excel puts opposite values on the future value and the present value. In section 6.3, we're going to talk about the future value of annuities. Annuities means that you have equally sized, equally spaced additional payments coming into an investment. So to review, we have a present value, that's the amount at time 0, and we have equally spaced payments that could come in, and then the future value is on the day of the last payment, because we are always talking about payments at the end of the period. So here's the first period, payment comes at the end. The last period, payment comes at the end. That puts it at the same time as the future value. We're going to take a $5,000 initial investment, and then we're going to make additional deposits of $1,000 at the end of every 6 months. We're going to have 10% interest and compounded semi-annually. So the compounding on the interest always has to match the spacing of the payments for us in this class. So one time, let's do this all the way out and see what it looks like. We take $5,000. We advance it forward 1 period worth of interest. This was 10%, but semi-annually, so it divide it by 2. So I get 5% plus my original 100%, which means that after 6 months, I have a value of $5,250 in that account. And then I'm going to have a payment, which will add an extra $1,000 into the account. Now I have $6,250. $6,250 will advance and get another 5% for the second half of the year. So at the end of the first year, I will have a value with interest of $65.62.50. Then my next payment comes in. Then I have $75.62.50. I let that advance for another half of a year. I get another 5% plus my original. Now it's worth $79.4625. Then my third payment comes in. We're up to $89.40.625. Advance it for the last 6 months. It will get its another 5% interest and grow to be $93.87.656. The last payment comes in on that day. We now have $10,387.66, and that is our future value. So we have deposits that are adding on to the initial principal. Let's try this in Excel. So in Excel, you have to create a frame of reference. I'm going to take the point of view of the investor so that the present value of $5,000 was money that left my pocket. I'll make that negative $5,000. The payments are an additional $1,000 leaving my pocket, so I'll make those negative. Annual rate, 10% for 2 years, compounding twice a year, semi-annually. The number of periods in total will be 4, and the rate per period would be 5%. Then I can find the future value. And this will add up all of the interest on the present value with all the additional payments coming in. I just need to tell it the rate per period, number of periods, payment, present value, and the type I can ignore. There's the $10,387.66, which is the same that I got when I moved the money forward every 6 months individually. What I want to point out is how the present value and the payment are working together to grow the account. So they need to have the same sign because they're doing the same thing. They're both going into the account. Okay, now I want to go back and I want to do this again, but this time, instead of having deposits of $1,000 going into the account, I want to take out withdrawals. At the end of every 6 months, I'm going to take $1,000 out. I still have 10% and it's still semi-annual, so 5% every 6 months. Here's what it'll look like. $5,000 advances, earns 5% interest, and I have $52.50. But now I'm going to take out $1,000, which leaves me with $42.50, and then that much money will advance for another 6 months. With interest, I'll have $44.62.50. But then I take out another $1,000 withdrawal, leaving me $34.62.50. Let that money advance for another 6 months. With interest, it grows to be $3,635.625. I make a $1,000 withdrawal, leaves me $26.35.625. And then for my last 6 months, the $2,600 with interest becomes $27.67.41. I take out my last $1,000, which leaves me a balance of $17.67.41. That is my future value. It's the amount in the account on the last day, the same day that I made my last payment. Okay, so in Excel, they call it payment, but it could be positive or it could be negative, depending on if you're depositing or withdrawing. From the perspective of the investor, present value would be negative $5,000 because that's money going out. But then the payment would be a positive $1,000 because it's money coming back in to me. So the present value and the payment now have opposite signs because they're working against each other. The $5,000 present value is trying to accrue interest, but then the payments, those withdrawals, come along and cut out $1,000. Let's see what this looks like in Excel. Present value, negative $5,000 out from my pocket. Payment, positive $1,000 because it's money that I receive. Still 10% interest for 2 years, compounding semi-annually, 4 periods, 5% per period. So everything's the same except that the payment and the present value now have opposite signs. When I go to find the future value, 5%, 4 periods, positive 1,000 payment, negative 5,000 present value, ignore the type, 1767.41. So that's a very different answer than I got when I was putting in deposits. Okay, so you really just have to take a viewpoint. So let's consider ourselves to be the bank. Then that present value is being received by the bank, so that would be a positive 5,000. It's coming in to the bank. And then the payments, they're withdrawals. Now if I'm the bank, those payments are leaving me, somebody's taking it out. This becomes money going out from the bank. So from the point of view of the bank, I could have positive $5,000 coming in for present value. Then my payment would be a negative $1,000 going out from me. Still 10%, 2 years, compounded the same. And there's my future value. Now notice that now the future value is negative because to clear out this account, in the end, the future value of $1,767.41 goes out from the bank when they come to make their final withdrawal and collect the value in the account. So you just have to take a perspective, and generally I like to use the perspective of the investor, but you could do either. And the payment and the present value just depends on if they're working against each other or if they're working together. Let's go to WebAssign. Let's take a look at problem number 3. This is Jake Werkheiser. He decides to invest, now read this carefully, $3,000 in an IRA at the end of each year. So that's not a present value of $3,000. That's $3,000 at the end of each year. That's the payments for each of the next 8 years. If he makes those investments, he gets 11% and it's compounded annually. So yearly payments, yearly compounding. How much will he have at the end of 8 years? That's what I'm trying to figure out is the future value, the value at the end of 8 years. Present value, nothing. No lump sum put in originally. $3,000 invested. I'll take Jake's point of view, so that's money going out from me. Annual rate is 11% for 8 years. Compounding once per year. So the number of periods would just be 8, and the rate per period would be 11% because it doesn't get divided. Future value, 11%, 8 years, $3,000 payments, no lump sum to start it off, no seed money on this one. And the type, you can put 0 or ignore. Jake will have $35,578. Okay, now state whether that's an ordinary annuity or an annuity due. For our purposes in this course, it's always an ordinary annuity. That means that our payments are coming in at the end of the period. It means that we use the Excel default 0 for the type. Everything we do in this course is always an ordinary annuity. Your finance teacher will tell you about annuities due. Let's go back to number 2. $1,500 is deposited. So I'll make that a payment, and it's going to go from me. So $1,500 each quarter in an account that earns 5%. That will be my annual rate. Compounded quarterly, 4 compoundings a year. After how many quarters will the account contain $100,000? So I want to have $100,000 come back to me at the end of that investment. I don't put in any seed money, so my present value is 0. And after how many quarters? Okay, let's see. Years, I don't know. Number of periods, I don't know. That's what I'm trying to find out. Rate per period will be my annual rate of 5%, but it will get cut into 4 equal pieces. Okay, what Excel can solve for me? It can't find the years, but it can find the number of periods. Number of periods will be equal to, I need a formula in Excel that will calculate the number of periods. So I don't want the future value formula. I don't want the PV, present value formula. Guess what they call it? They call it N per. There it is. The N per formula, I need to tell it the rate. Again, that's per period. The payment, which was $1,500 deposits. Present value, no money up front, no original seed money. I want it to grow to be $100,000. And the type, end of the period, 0 in Excel, ordinary annuity is the finance term. 48.79, and that's the number of periods. So that's 48.79 quarters. And it says to round up, which would be 49. Okay, let's look at number 6. This is a recent college graduate's first job, allows her to deposit $100 at the end of each month in a savings plan that earns 12% and it's compounded monthly. That continues for 8 years, and then it's impossible to continue. So she stops paying those $100 deposits. The accrued amount after the end of those first 8 years remains in the plan for the next 15 years. No additional deposits or withdrawals after that. How much money will be in the account 23 years after the plan began? Let's map this out. This problem is divided into 2 parts. We have the first 8 years. For this part, the present value is nothing, so no seed money, but then she makes deposits, payments of $100 each month for the first 8 years. The second 15 years, for a total of 23 years, there's no payments. So anytime the interest rate changes or the payments change, you have to break it into 2 completely separate problems. So I'll take this first part of the problem and I'm going to figure out the future value that will be on the day that the last $100 comes in, which is the end of the 8th year. Future value, I'm trying to figure out. Present value 0, no original seed money, $100 leaving my pocket, annual rate of 12% for the first 8 years, compounded monthly, so that will be 12. Okay, the number of periods will be a total of monthly compounding, total of 12 per year for 8 years. Multiply those together, that's 96 months of payments. And then the rate per period is the annual rate divided into 12 equal pieces, 1% per month. So then I can find the future value. $1%, 96, $100 payments, no lump sum at time 0, ignore the type. There will be $15,992.73 in the account at this point. Okay, now this money is going to carry on for the next 15 years, but now the payment is going to be 0. And looking at the last half of this problem, then the future value from the first half of the problem becomes the seed money. It's the present value for the last half of the problem. I'll take my future value and make it a present value, and I'm going to consider it as a negative present value. Payments for the last half of this, for the last 15 years of this investment are 0. It still stays in at 12% for 13 more years, 15 more years. Compounding monthly. The number of periods should have automatically updated. Monthly compoundings for 15 years gives me 180, and the rate per period is still 1%. Then I want to find the new future value at this point. Future value, 1% per month, 180 months. I now have no additional payments going in, but I start off with $15,000, almost $16,000 in the account. End of the period. Total at the end will be $95,889.24. So if you start a retirement plan early, I mean, $100 isn't really that much when you consider retirement, and then nothing, but it still grew to a pretty good amount just because time is on your side. So that's why they always say start early for retirement. 95, 889, 24. Let's do one more together. This is another one of those kind of two-part problems. And just a note of warning that the watch it, the publisher doesn't use Excel. So they're going to use formulas or finance calculators or something, but Excel's a lot easier. Okay, in this problem, a couple is going to deposit $700 at the end of each quarter for the first 8 years, 9 years. So my last payment of $700 will come in at the end of the 9th year, and then after 9 years they start a family and they can only contribute $200, still per quarter after that. They leave the money from the first 9 years in the account and contribute $200 for the next 18 and a half years. How much will they have in the account to help with their child's college expenses? Well, anytime the payment changes or the interest rate changes, you have to cut the problem into two pieces. So for the first half of the problem, present value nothing because there's no money right here at the beginning. The payment will be negative 700. My rate is 7.8%, but that has to be cut into quarterly compoundings. And my number of periods will be 9 years of 4 compoundings each. Let's put that part into Excel. Present value, payment, annual rate for 9 years, compounding quarterly. Number of periods will be 9 years times 4 quarters per year for 36. And the rate per period, 0.078, but that needs to be cut into 4 equal pieces so that you have per quarter 1.95%. Then my future value. If $36,048.08, and that money is sitting right here at the end of those 9 years. Okay, now I want to do the second part of the problem for the next 18 and a half years where I have these $200 payments coming in. So for the second half of the problem, so ignore what happened at the first part, and this is what it looks like. You now have a present value of $36,000. And then you have additional payments of $200. Okay, now the present value, it's my money, and the $200 are my money. So you have to think of them as working together. So if the payments are going to be a negative 200, they're working together with the present value. So I would make that a negative 36,048.08. This is okay, so present value at the beginning of this last half payment, negative 200. Annual rate, the same years, is 18 and a half. Still compounded quarterly. My number of payments should have updated. 18 and a half years of 4 payments per year gives me 74 payments, and the rate per period remains at 1.95%. My new future value. Rate, number of periods, payment, present value, yes, make sure they have the same sign, type, 183,000. $64.19. Okay, I hope this makes sense, and let me know if you have questions on Excel or on these annuities, and I will see you in class.